Welcome, everyone. Good morning, good evening from wherever you're joining. Maybe good afternoon for some of you. I'm joining from India. And like Alex mentioned, this is Lavi Nigam. I'm developer relations and engineer or ML engineer at Google Cloud. And one of the things that we'll talk about today, and one of the very favorite topic of mine, is essentially how to build question answering systems which are multimodal in nature, or essentially in a very small keyword, how do you sort of build something like multimodal RAG? Now, before I start the session, there are a couple of things. Feel free to sort of ask your questions on the comment, like Alex mentioned. I don't look at the questions all the time, but I'll take pauses in between. The way this whole session is divided is that first we'll go through a couple of slides. I know some of you will get bored, but it sort of will help us sort of understand the whole context, understand the architectures and the flow. So we'll spend a good bit of time initially to sort of cement the whole architecture. Then we'll go to the notebook, of which I'll share the link with you very soon. But if you see the comments, you'll see that this has already been flagged at the very top, so you can actually just open the link right away. The interface that we're going to talk about to implement multimodal RAG or to work on multimodal RAG is Google Cloud. And the Gemini and everything that we're going to use through Google Cloud. Now, that notebook has pretty much everything that you would need to sort of build something like multimodal RAG, which we'll walk through. But it doesn't stop you from implementing the same thing with, let's say, normal Gemini API, which is outside of the cloud. So if you're somebody who's like, hey, I don't care about cloud, I just want to use, let's say, normal Gemini models outside of the cloud, you can sort of change those things in the notebook itself. It'll be a bit of work, but you should be able to do that. If you want to run the same notebook at your end, the one that I'll walk you through, again, this is not the hands-on session, so I don't expect you to work or run the code with me. But if you do wish to sort of rerun the notebook later after the session, you would need Google Cloud account or credits to be there. So be very careful when you run this at your end with the account, with the project ID that you have. It will incur cost because we are sort of hitting up different APIs, we are hitting up embeddings, we are hitting up Gemini and all of that. So be very careful. And again, like I said, you do have a choice. If you do not want to run this on cloud, you can sort of run this outside of it, right? Okay, with that said, again, feel free to post your questions. I'm going to take pause in between the sort of couple of slides just to sort of take the questions. If there are no questions, I'll continue. We'll also sort of spend a lot of time towards the end just to take any general questions that you have. With that, let's get into the topic, right? Okay. So what I typically do, and also one of the things which I forgot to mention is that maybe my video might go eventually because I'm trying to sort of optimize the bandwidth. So you might just see my screen and will hear my audio. I might sort of come back maybe towards the end to take the question. So just be ready for that as well. Okay, so before I start the topic, I usually sort of try to set the context to why do we need things like RAG and why do we sort of need something like multimodal RAG. And a lot of you might already know this, like you may be aware of what RAG is, but still, sort of from a general perspective, let's try to paint a picture. Why would you want to do something like that? So I start with a very simple example, which is when you sort of use any LLM, again, irrespective of whether it's Gemini, ChatGPT, Anthropic, anything, most of the work that we do is essentially we are trying to ask questions. Either we are trying to sort of summarize an information, we are trying to ask a question answer with publicly available data, we're trying to sort of generate poems or some kind of data based on the data that you input. But all of this is sort of centered around the data which it has been trained on, right? So one of the things, this is one of my favorite example which doesn't work right now. So if you were to test this on any LLM, you would get the correct answer, which is on the right side, the green one that you see. However, not so far in past, as you can imagine that the years in AI world is something which is very short-lived. So not long back, when we used to search for questions like what is LangChain, because of the cutoff dates of many of the models, you used to get very different results. Like, for example, one which, at least, and I've seen this, this is not sort of fake, I've seen LLMs giving this answer, is that if you were to ask what LangChain is, it used to tell you that LangChain is a blockchain based platform. Now, again, if you know what LangChain is, you know that the left answer is wrong. It has nothing to do with blockchain in general. In fact, the right answer, which is the on the right hand side, is the correct one, which is that LangChain is an open source chain framework which can help you build amazing applications without the need of any specific LLM. So you can choose any LLM that you wish to, and things like that. And this is what brings us to one of the very important points, which is many LLMs, they do have their cutoff dates. They are being trained on very different data which are essentially in the public domain, or let's say the companies have access to it. And that is what the premise of the problem that we are trying to solve, which is that in an enterprise, there are many times that you have a need where you want the generations of the model or whatever you're asking as a question has to be grounded on the data of the enterprise. To make that sort of picture more clear, let's call that as private data, right? Any organization will not have their private data indexed on the internet unless, of course, you have a direct partnership with those companies and you're actually willing to share those uh, data sets with the company that they can train LLM on. So let's assume that we don't have that, and the private data is a data which nobody has access to except the business people and the people who rightfully have the access control. And these can be different kinds of data, right? So the unstructured, they can be unstructured data like PDF, PPTs, Excel, doc, HTML, audio, image, video, any kind of unstructured data that you can imagine. It could also be sort of different APIs, maybe APIs to get to a certain specific data. It could be structured data sets from the databases, vector stores, knowledge graph. It could be different files like JSON, CSVs, and all, or it could be any other enterprise system. So you can imagine the whole scenario that the reason we need systems like RAG is because we want all the grounding, or let's say the generation of the LLM, to be 100% grounded on the private data that we have, data which the LLM is not aware of, but we want the reasoning and the generation to happen based on that. So it doesn't hallucinate the information that we want it to learn. And that's the very basic premise of sort of what RAG is. And again, like if you know this, you would know this already, so it's not a revelation to you. But if you're sort of going through this for the first time, at least you have a context that, okay, we don't care so much about what we can directly talk to these chatbots and for example, Gemini or Chat GPT and all. It is more about that the private data, the data that I have from an enterprise perspective. How do I talk to that data? How do I ground every generation based on the data so that it doesn't sort of hallucinate any of those things? Now, if you think about that problem for a second, there are many different ways to solve that problem, even before sort of doing the RAG. So it's not that RAG is the only solution to solve that problem, or RAG is the solution to any kind of hallucination. One of the other thing which I also want to make very clear is that hallucination is not bad. Hallucination is a property of the model. Unlike a lot of people who believe that to be a bad thing, it's not a bad thing. It's essentially a property of the model where it is trying to be sort of generating things, new ideas, and new things. So you need that property many times. For example, when you're writing code, you want your models to sort of be creative, be hallucinatory in terms of different things it can do. The thing that we are all sort of not so happy about is that when it makes up something which doesn't exist, right? So the only thing that we need to remember about hallucination is that one of the properties of hallucination, where it makes up something which doesn't exist either in the real world or in the enterprise world, is where you have the problem. You do not have the problem when, based on the entities that exist in the real world or the enterprise world, you still want some kind of a creativity around it. So just to give a simple example, let's say you're trying to build a Python program using any LLM, and you want it to take certain data, which is again your enterprise data. You're fine as long as it sort of grounds itself with all of those data sets, right? And it does different variations of the logic that you're trying it to build. So let's say you're just trying to add two numbers. As long as it stays within the limit of what the addition looks like, and you want it to be as creative as possible to solve that problem. So you need that hallucination or creative control in that, right? So it's very important to remember, because a lot of time people assume that hallucination is bad all throughout, right? It's not bad as long as it is grounded, based on the data that we have. So the naive solutions that you can do right now is you can actually fine tune the data. You can fine tune the model. So you can take either open source models, you can take closed source models, Gemini, ChatGPT, GPT-4, GPT-3, and all of those models, Anthropic. And you can sort of fine tune all of that with the data that you have as a private data or enterprise data. Now, of course, as you can imagine, it's not straightforward. Um, you would have to sort of spend a lot of money, you would have to spend a lot of engineering effort to sort of build something which can work. So it's not a good immediate solution, but it's a solution that will work in the long run. So you'll not get something right out of the box. And that's why fine tuning, while a good solution, it's a solution that you would prefer doing it at longer scale. Like, okay, fine, maybe 2 years down the line, I do not want to do this so many different sort of nuances of the solution. And I keep sort of building up the data sets so that I can finally tune it. You can also sort of make the humans or the subject matter experts sort of check each and every input and output. That's another way to sort of control the hallucinations and make sure that you're able to get the right answer. And the third is the prompt engineering, which again is like the most first way of doing things, which is maybe you give examples in your prompts, maybe you give instructions in your prompt, maybe you add the behavior that you're expecting it to work on. So these are sort of some of the ways you can sort of build the solutions. But again, like I said, these are all the naive solutions. These are things that you can do to start. Now we'll come to the RAG part, right? And slowly we'll also sort of move in the multimodal RAG part as well. Now let's talk about RAG. So, like I said, the problem is, at least the problem that we are trying to solve is that all the LLMs, the limitations with them is that they do not have access to proprietary, or let's say, the private data. So we want all the benefits of LLMs, all the intelligence and the reasoning capabilities of these LLM, but we want it to be connected to the source that we want it to know, right? And then everything, all the other intelligence would be grounded on that. To do that, there are two major components of the RAG architecture. And again, I can sort of spend 3 hours just to talk about RAG in detail. So we'll sort of take things at a high level. There's a lot, many things, there's a lot that goes into details of it. But let's talk about two major component of it. One is the retriever and the other is the generator. Now, when I typically try to sort of explain these two things, I always love to take example of Google search for obvious reason, but also from a from a perspective that we all sort of do Google search, right? So think of it that in the world there exist trillions and trillions of websites and content which exist across sort of different countries and different domains. And Google sort of indexes all of this information every second. So every second, every new update in the website, every new content that gets created, Google bots are sort of indexing all of this information in the backend, right? Now, this is what Retriever does, which is just like when you search for something on Google search, out of the trillion indexes that has been created, the top 10 results are being sort of picked. And again, there's a page rank algorithm that helps you do that, or there's a lot of algorithms that helps you find the most important top 10 links. But you get the idea, right? The idea is very simple, that out of the trillion possibilities, you get the top 10 closest possibilities to the question that you're asking. And that's what the goal of the retriever is, that whatever question you ask, whatever source data that you have, in this case it is private data, among the oceans of the private data that you have, retrievers are built to find those important information, so that you now focus on those top 10, top 20, whatever that number that you want to. And that is your, you can think of it as a needle in the haystack, right? So out of all oceans, this is the one which is relevant to the question that you've asked. So that's the component number one of the RAG. The component number two, and this is where it goes beyond Google search, right? Because in Google search, you get the top 10 link, and the duty is on you to figure out inside those links whether the content sort of makes sense to you or not, whether what you were asking is properly addressed or not. A part of it is now sort of part of the AI overviews that you get. So when you ask for what's the nutrition value in avocado, typically Google AI overviews will give you that at the very top. In fact, Bing also sort of does this. So most of the search engines are trying to do this right now. But the generator part is very important, because what we do is that the top n that you have selected out of the oceans in the world, you send those top n to the LLM and say, hey, the user was asking this question. Here are the top 10 results, which looks very similar to the question. Can you frame the final answer so that user gets to, gets to the query that he or she started off with? And that's what the component of generator is. And you can use any LLM that you wish to. We are going to use Gemini here. But these are two major components of RAG architectures, and this is what we'll sort of end up building. Now, one thing here is this is typically, this works wonderfully well when you are only dealing with text data. The other power of this architecture is that it works exactly similar if you also work with multimodal data. And we'll see in a moment how that happens when I'll walk you through the whole thing. So the way, again, if you remember the generator part of the architecture, the prompt in that looks like this, where you sort of start with the persona of the instruction, where you specifically say, hey, do not answer unless you find that in the context. And the context here is, again, the retriever has found those top n values among the ocean of private data. That is what is passed in the context, and then whatever the question that user has asked, now you're essentially posing this question back to the LLM, because LLMs are good and they're intelligent in order to sort of frame the final answer, right? So that's the kind of prompting that you do, and this is what we say, the very vanilla RAG prompt that you have, which is you have a persona, you have instruction, you have the context, which is the most close relevant information of the question that you have asked. Then you mention the question, and then you ask Gemini or any other LLM that, hey, can you now sort of frame the final answer based on it? One of the very important things in this prompt is, if you see this part, if the context is empty or it doesn't sort of make sense, just say, I do not know the answer. And this is very important. While it looks very trivial that, hey, this is like, of course, I'll add that. But it's one of the very important things, because again, we know that LLMs are intelligent and they may sort of establish some connection between the relevant files and the question. So you have to be very careful, and that's why we put this sort of statement there, and you can come up with more creative ways of putting it, that if you do not find that the information at all makes sense to the question that the user is asking, please do not answer, or just say, hey, I'm not confident in giving this answer because I don't have very good results. And later we'll also see sort of how we also have a control of this with numbers. So later we'll see how semantic similarity sort of also helps us understand the confidence score. So you can actually, if you get confidence scores less than a specific threshold, you can just say, hey, I can't get to this answer because I don't have any relevant information that I could find, right? So this is the modified prompt. This is the prompt that we're going to use for this. Okay. Now, taking a step back, one of the things which we'll go through the detail of this architecture. This is an architecture which is directly coming from LangChain. Again, credit to LangChain for this. But let's see how these two elements are built from an architecture perspective. So there are two stages to it. One is a batch process, which is the ingestion process, and the other is the process which we do at the query time. Again, take the example of Google search. Just like I said, that in the Google search, what is happening is that in the backend, a lot of indexing is happening over the world. Every time there's a new website coming up or there are new content on the website, there's a backend process of indexing. All of that is happening. Very similarly, we'll also try to do this for the RAG system that we are building. So what we do here is we ingest the documents, we split the documents into smaller chunks. And the reason we do this is because not everything in the whole document might be relevant. Maybe there are some smaller chunks which are more relevant to the question that we ask. So just to be on a safer side, we put everything into a smaller chunk. Now, it's a whole session in itself just to figure out what should be that chunk size, because it goes into a lot of machine learning. It goes into a lot of mathematical details that you would have to figure out in terms of plotting different graphs and things like that. But let's assume for a moment that we're going to just do the simplest 500 character chunk or recursive chunk, as some of you may know. So you do some kind of a chunking. It could just be paragraph chunks overall. And then you build embeddings on those chunks. Now, Again, for those of you who know what embeddings are, you know what they do. For those of you who do not know, let's just take a very simplistic approach of understanding. So, embeddings are those algorithms, they are deep learning algorithms, which can take the data that you have and then give you a number representation of that data, such that with that number representation or vector representation, you can combine two chunks and then measure whether they are similar or dissimilar. So imagine if you have millions of chunks and you want to find what are the chunks which are very similar to each other semantically, not sort of by the usage of the word and all. You need something like embeddings, because embeddings are great at doing that. Embeddings are great at finding semantically similar chunks to the given chunk. And you'll see later that how this becomes the most important aspect of the architecture, because when the user is going to ask question, you're going to actually go back to each and every chunk and do this very small calculation and say, okay, let's just do semantic similarity with all the chunk and give me the top chunks which have the highest similarity scores. And depending on the algorithm that you use to do the semantic similarity, the most common is cosine similarity. Your values could be between 0 and 1, minus 1 and plus 1, and things like that. So higher the score, better it is. It means that you are more close to that chunk semantically. And this is very important keyword, is semantic similarity. So this is what you do on the left side. And then you store this whole thing in a vector DB or vector store, any kind. In our case, we'll sort of use the pandas data frame. On the right hand side, like I said, you ask a question, you convert that question again to embedding, because you want to find that question semantically similar to which embeddings or which chunk. And you do that, and then that's how you get those top 10, top 20 chunks. And then you feed all of those chunks back to the LLM and you get to the answer. And this is how sort of the overall flow of sort of RAG works, right? Now, I also want to sort of quickly talk about the flow that we'll also follow. So this is what you just saw is a typical RAG flow. Let me also show you what the flow that we have followed to solve a specific problem. So again, we do something very similar. So on the left side, we do the batch process. So we take the data corpus, we process them, we store it in a simple pandas data frame for the simplicity. On the runtime, and we have not built the interface, so we'll skip the interface. But on the runtime, you again get the query, you take that query to the data store, you filter the data, you rank the data, and then you use LLM, get the answer, and you evaluate. Now, just to show you what does the pre-processing looks like, again, we have talked about this, but this is more detail in a sense that you take any kind of modality of data, you convert all of those modalities to a representation of text. How do you do that? This is where Gemini comes into picture. See, there are two very important features of Gemini, one of which is that it has capacity to process multimodal inputs. You send a text, you send a PDF, you send a audio. And when I say PDF, it means it has capacity to learn through the charts, the graphs, and everything which are there as part of the PDF. You can send the audio files, you can send the video files, you can send the images. So it has capacity to learn through all of that. And of course, the output is limited to text, so it doesn't output the other modalities. The multimodality is for the input. So what we do is we take all of this as input. We use Gemini for non-text sources. So you can see that for the video, for the audio, for the images, we actually send those to Gemini. We extract the transcripts and the summary of video and the audio, because now we have that in the text format. Same we do with the images, which is we take the image description with context and we save it in the image text format. Now, with the PDF, we already have everything as text, so we can convert everything into summaries and descriptions and text. Now, what we have done is we have taken all the multi-modality inputs. We now have representation of all of that in the text, and that text we then do the chunking and we build the embedding, just like you saw in the previous flow, and that's what becomes our the very core data store that we have. This is very important because this is what we are essentially going to build, and this itself gives you so much power to build things over this. Once you have built your data store or vector store, whatever you want to call it, with different kinds of data inputs, half of your problem is sort of solved in that sense, because you just need to send this and then get the best chunks out of it, right? Now, this is the flow of how would you do the runtime. So again, the same thing that we saw. So you take the user question, you take the cosine similarity with the data store, which gives you the relevant chunk. You rank the relevant chunk by top 5, top 10, and things like that. Then you send those chunks to LLM, you get the answer, you evaluate the answer. Now, of course, you can also evaluate the answer if you have the ground truth data. So this is out of scope at this point because we don't start with the ground truth data. So we'll skip that particular part. Okay. One quick thing, and let me sort of take a quick pause just to see if you guys have any questions. Dinesh is asking how much cost roughly we expect if you run the notebook on Google Cloud. It'll not be more than $10, Dinesh. Everything less than $10 should be there. The recording will be available. Yes. Okay. Perfect. So coming back to the presentation, again, Google Cloud is a huge ecosystem, and you know that there can be so many things that you can do. Uh, there are many different ways you can build RAG on cloud. What you see here is again those two specific component. You have a retrieval component and the generation. In retrieval, you can either use a software as a service, or let's say out of the box Vertex AI search, which is Vertex solution to build that. If you want to, if you do not want to build your own and you just want to rely on something built for you to do all of this, you can also sort of build this on Llama Index. You can also do this on LangChain. All of this is sort of provided as a hosted solution. You can also use Google search to ground the information. So if let's say you want it to be grounded to whatever happens on Google search, you can also do that. What we are choosing to do is we are trying to bring our own retriever and retrieval, which means to say that we build everything on our own. So this is just to show that you're not restricted in terms of how you want to build the solution, whatever your choice. And we are picking the choice, which is we try to build this on our own. For the generation, again, you have many different options. You have open source models like Llama, Anthropic models, and things like that. In the example that we'll take Gemini for that, right? Um, and this is what the whole flow is. So we take a simple PyPDF parser to do the layout parser. We're going to use simple pandas data frame to do the index and the retrieval. We're going to do the ranking through cosine, and then we're going to do the generation with Gemini. Now with that, what I'm going to do is I'm going to quickly jump to the notebook. And before I do this, again, the link of the notebook is there already tagged. I think Alex has tagged that on the comment section. If not, okay, you see that there. If not, you can scan this QR code. What this QR code will do is it'll take you to the notebook that we'll talk about, and that's the notebook that we'll be using. While you do scan this and open this up, let me sort of address quick questions. Does different embeddings have different outputs? Yes. So different embeddings will have different outputs. So the one that we'll use is the Vertex AI embeddings. But if you were to use any other open source embeddings or embeddings from, let's say, OpenAI or any other sources, they will have different output in a sense that you'll have different the way that they generate the embeddings are different. So the models are different, not so much difference in terms of the output. So if the embeddings are really powerful, you will get pretty much similar outputs towards the end. How they are used and how they build vectors and all is a separate thing. You will see some differences in the outputs towards the very end. But if they're really powerful models, you will sort of see very similar results towards the end. For RAG, how much is context window a limiting factor? So Jatin, I'll talk about this when we'll actually do the hands-on. But do remember that Gemini has 2 million context windows. So technically you don't need to do any chunking, but we'll talk about why you should still do the chunking, irrespective whether you have 1 million or 2 million. So we'll talk about that. Other question is, which vector database do you use? Which one's a popular choice? So the one that I use is very simple pandas data frame, because I'm sort of trying to go through a specific logic. But if you are inside Google Cloud ecosystem, you have many different options. You have vector search, which is one of the scalable versions. You also have options of Alloy DB, Postgres DBs, and all of those vector DBs as well. But it doesn't stop you. You can actually use outside of the Google Cloud vector DBs as well. So Pinecone, Hydra, and so many others which you have. You can use any one that sort of fits your budget. It fits your idea of the stuff. All of them pretty much does the same thing, which is they are good at storing vectors, they're good at taking out vectors, doing cosines, and all of those things. So whichever your thing is. um, all right, so let me sort of reshare the screen, and let's do the all right. Okay, perfect. So the link that I shared with you, and again, you have the link available on the chat as well, so you can just copy paste from there. But this is what it will open. Now you can run this notebook inside Google Cloud if you have access. You can run this in Vertex AI Workbench. You can run this in Collab Enterprise, or you can run this in normal Google Collab. What I'm going to do is I'm going to run this in normal Google Collab. What you need to run this, if you were to run this at your end, is you just need your own project ID. So if you already have Google Cloud account, you just mention your project ID. That's it. Rest everything just goes step by step. So you do your auth with your account, mention the project ID, and you should be able to run through the whole thing. If you do not have Google Cloud and you do not want to spend money, absolutely fine, no worries. The outputs of each and every cell is already there, so you don't technically need to run it. All the code is there, so you can learn through the code. You can see how things are done. That's second option. The third option, like I said initially, is um, this notebook is using Gemini, which is inside the cloud. You can actually change this and you can modify the code to use any other model if you wish to, because like I said, the focus here is the concept. So you can choose to change it to any other model of your choice, or you can use Gemini, which is free, the Gemini API from the Google AI for developers. So you can use those Gemini as well. So completely your choice, because the outputs are given already in the cell, so it's easy for you to, and everything is sort of written what is there, what is not there. So you don't genuinely need to run it if you're just trying to learn through it. Okay, so coming back, let's sort of go through it. The model that we are using is 1.5 Pro, 1.5 Flash. We're going to use two embeddings. We'll talk about this. One is the text embedding, and the other is the multimodal embedding. We are using the latest version of that. Now, let me talk about the input data, right? And this is where we sort of, set the context of why we need something like a multimodal embedding. So the first document that we have, I'm going to show you three documents. This is the first one, which is a Gemma paper, Gemma research paper. As you can see that this document is bunch of text, good enough for RAG. And we want to ask questions to the model, and then that model should be able to give us all the answers grounded on this research paper. So it should not make up anything. It should actually give me all the answers based on the input data that I provide. However, there's one additional thing that I'm trying to do here, right? What is that additional thing? That this paper has many different charts and tables. And this is what I always miss if I just do a simple text drag. So what I'm going to do is, and this is what we'll go step by step, is that we should be able to ingest these documents, and we should be able to take both the images and the text and everything else in that data into the data store, so that if my question has the answer which is available in the sort of images, I should still be able to get to the answer part, right? So this is one of the examples. The second document is a simple blog. This is a TPU training blog. If you see, again, it has a very interesting chart. It has an architecture, bunch of normal text which it has tables. Amazing. Tables are something which is very important, again followed by the text. So again, I have questions where maybe the question answer is available in the table. I should be able to build something where all of these things are considered. And the last example is the Med Gemini paper. Again, this is Gemini specifically built for medicine. This paper also has bunch of different benchmarks and charts and everything. Specifically this chart, if you see this one, this is sort of different benchmarks and how Med Gemini has been performing with respect to other models and things like that. And let's say my question is that, how Med Gemini performs with respect to other model on many different benchmark. The problem is that most of the information is available in the chart. If I just index the text, I'll not get the answer in a very good way. And that's what we are trying to build. That's the kind of system we are trying to build, which is, let's build a multimodal RAG with the concept that we just learned, and see how Gemini capacity to do multimodal input and 2 million context can help us build a system where we can feed these four documents, and we should be able to ask questions without mentioning where the information is available among those four documents, and get to the answer part, right? Okay, to do that, the very first thing that we do, and again, if you see in this whole notebook, um, it sort of utilizes a util function where the brain of the whole function brain of the whole notebook exists. So if you click on this, it will take you to a huge util file which has very simple Python functions, no fancy sort of decorator classes and all, very simple Python functions, which you can just copy, paste it into Gemini, ChatGPT, and get and ask it to explain it to you. It should be very easy for you. So, for example, if you notice here, I'm calling this specific function, which is get document metadata. You can simply copy and you can go to this util and you can just do a copy paste, and you can see that this is that function which I'm calling, and this is what that whole function is doing. Again, this is built to make it sound very simple. And again, because we are trying to sort of build this from the scratch, so that you understand what's happening. So the first thing that we do is, when we essentially try to get the document metadata, is that we pass those four files. What we want is two things. One, that we should have a parser which should extract all the text, not only the text, but it should also extract all the images which are available on the pages. Now, here's something very interesting that we do. So when it finds an image on a given page, we actually take that image and we send it to Gemini with this specific prompt. So what you see here is a simple prompt that we use. We say, hey, Gemini, here's the text on the page. I want you to act as an image analysis expert, and I want you to give me and explain me what's going on in this image, and make sure that the explanation that you give or the description that you give is grounded on the text which surrounds that image, right? So what I mean by that is, if you go to, for example, Gemma paper, it should take this image, it should see all the data which is among the image, so -1 and +1 of the page, if it is not the first page, and take all the context as the ground context, and then come up with a description of what that image is, right? So by that very simple logic, what we have done is, we can now sort of index the image as well, because we now have the description for it. So when you run this logic, what it does is it goes through the file step by step. So you can see that it is currently taking the Gemma technical paper, and it found an image on the page one. You can see that it is storing this image. So if you actually run this notebook, it is locally storing this image into this format, because it has to run through so many things and it's sending Gemini. So I've added a sleep function as well, so that you don't hit your quotas. Here's a second one where we are going through Gemini 1.5 report, and you can see that it is extracting images from so many different pages. And remember, every time it is taking this image, what it is doing is, it is taking this image, it is using this prompt, and it is sending this along with the text it has found on the previous and the next page along with that page, and sending to Gemini and saying, hey, help me create a description of what's happening in this sort of image. It could be a chart, it could be a table, it could be anything. Whatever that is, Gemini is very good at extracting those things. And because it shouldn't hallucinate, we are grounding it with all the context which is around that. So when you run through this, and this takes sort of, I think, 5 minutes. Yes, so somewhere around 6 minutes to process those four documents. Um, and just to tell you, those documents are not small, right? Like if you see, one of the documents, especially the Gemini Med Gemini paper, is 58 pages. The other one is again 58 pages. So we are roughly processing 200 pages. And that's why, to process those 200 pages, we were able to extract all the text from each and every page. We were able to extract images, and we were able to send those images to the Gemini. All of that we were able to do in 5 minutes. Again, the goal is not to optimize it. I'm sure all of you are smart. Some of you might actually reduce it to maybe 10 seconds or 20 seconds. There are ways to do that. So the goal is not that we're trying to optimize it, optimize. The goal is that we are able to build this pipeline where we can get to this. Once you do that, let's see the output. So it gives you two metadata, and this is, you can think of this as data stores, two data stores, one specific for text, which is what we are calling as text metadata DF. What you see here is you have a file name, you have a page name, you have the text on that page, you have the embedding of that whole page, but you also do one step ahead. You divide the whole text and the data into different chunks. So what you see here is that the whole page data is divided into five chunks of 500 characters, and that's what the chunk text is. And then you also have the embedding of that chunk. Now it's your choice. You can either use chunks to find the relevant information, or you can say, I'm just going to match it with the whole page. I don't care about the small chunk. It's completely your choice. Typically, you'll find better results if you were to do this at chunk level. And again, there's a whole science behind how to find the best chunk and all of that. We'll not go into that. That's out of scope of today's session. But there's immense amount of material over the internet that talks about that. That's the first one. The second one is image metadata. Now, this is very interesting. It is exactly same as text, but this is specifically for images. So again, you'll see that you have a file name in that page. There can be multiple images. So it found one. So you have a counter of that. You have the path of the image. You have the description which Gemini gave you. You have two embeddings. You have a multimodal embedding of the image itself. So if you're trying to find, let's say, similar images given us input of image, you can actually use multimodal embedding. If you have a text and you're trying to find the images similar to the text, you will use the text embedding. So you have those two embeddings available to you. Do remember in Google Cloud, you have actually two embeddings. One is text embedding and the other is multimodal. The multimodal embeddings can be used for images. So you send the image and you get the output as the numbers. You can also use the multimodal embedding to convert the videos into numbers as well. So if you want to find similar videos, similar images, multimodal embeddings are very helpful, but they don't work on the text. So for you to work this on the text, you would have to first extract the descriptions of those images, videos from using Gemini or any model, and then you use the text embeddings to sort of get to that. So these are the two components. Okay. So now that we have these two data stores, and that's where I said that if you build that, 60 to 70% of your work is done, because now you have the metadata, your data store has all the citations. Now you just need to sort of combine things together. So let's start with the same question that we started off with, right? The one that I gave you, that let's say my question is, what are the various Gemini medical benchmark that shows its performance relative to the other models? Now, what I'm going to do is I'm going to sort of use the embedding chunks. I'm going to use cosine similarity. Again, you can sort of just copy this function, go to the utils, and you can see what this function is doing overall, just to see how I'm getting to the cosine similarity and all. So you can see here, I'm actually calculating the cosine scores with the metadata that I've been passing, and I'm trying to match it with the chunk in the text. So when I do that, the top match that I get, and this is a cosine score, so I'm getting this at 0.78, is automatically from the document which is Gemini, page number 29, specifically the first chunk. And this is what the chunk says, right? So it has some of the benchmark that I'm asking for. Again, remember that we have already seen this data. So if I again go back and show you, the question that we asked, and we have sort of framed it in a way. But the question that we have asked is essentially coming from this table. So we know for the fact that we'll not be able to get to the answer just by using the text chunk. But let's try it a bit more. So let's say you were able to find the top three chunks. So you can see that I'm taking the top three chunks based on the question that I asked. I put a very simple RAG prompting and pass all the top three inside that. And I call the model, which is 1.5 Pro. And the funny thing that you'll see here is you essentially tells you that, hey, the passage mentions that the Gemini models are evaluated on 14 medical benchmark, but it does not enumerate the specific benchmark. That's true. That's true because again, we know we are trying to game the system, right? It's true because the answer is available in the image, so we'll not get the actual values out of it. Similarly, I try the flash model as well. It gives you exactly the same answer that hey, it was done using this, but I can't get to the actual part. All right. So then we see the next part. So we say, okay, we can't do this or we can't get to the answer using the text part of things. Can we use it? Can we use the text description that we got on from the images? So now we use the same query. So you can see that we still have the same query. This time I'm using text embedding from the image description. And what I'm trying to do in this case is I'm not trying to get to the answer, but I'm saying, hey, given this question, can you tell me all the images which are relevant to the question that I asked? And that's what I'm doing in this place. Once I do that, it gives me these bunch of different images, and you can see that it's getting close. It's getting close. It was able to figure out. And again, why is this happening? Because Gemini was able to explain this. In fact, if I were to show you, this is what Gemini was able to sort of extract. Sorry, not that. This was the page text. This is the definition. This is the explanations of that graph that Gemini was able to create. So it tells you this is the X and Y axis. This is the five distinct method which are being compared. So it has that information, and because of that, and because you're doing the cosine similarity with that, it gives you back the images which are closer to it. So this is good. Now at least we know that the question that we were asking, the answers might be available in this image. So that's the part one of the puzzle. The next thing that we do is we again do a RAG, but this time we do a multimodal RAG. And we can do this because Gemini can process a larger quantity of context. So we are not limited by the context here. We can actually pass multiple images. In fact, you can pass 3,000 images at a given time. That's what the 2 million context sort of helps you do. And the second is you can actually pass the combination of text and the image together. So what I do here is all the images that I found in the previous example, I actually create a simple string saying here's the image, which is the object of the image. Here's the description of that, which is the description given by Gemini. And I put all of that in a simple RAG prompt, and then I send it to 1.5. Now when you see the answer, which, and it took 13 seconds to do that, and it sort of goes up and down. Sometimes it takes 20 or maybe less. Now when you see the answer, this is much much better than what we were getting in the text, because now it goes through each and every benchmark it has. It goes through each and every image that you sent, and it tells you overall that okay, this is how Gemini is compared to other models and other different benchmarks. And this is very powerful because now what you're able to do is, again, remember, you just asked a simple question and it was able to figure out the specific graphs which is going to give you that answer. And you didn't tell it where those graphs are available, right? At no point you mentioned which file or what files. It was able to figure all of that out because of semantic similarity and the data store that you had. And here's how you were able to sort of build through that and do this at scale and then get to the answer part. Now I'm going to show you the last part. I'm going to skip a couple of things in between. I'm going to come to the last part, which is very interesting. Then how do you sort of build this at sort of more automated scale? Which is, let's imagine that you have a query like this. Again, you don't know which document it is, you don't know where the answer is available. The answer could be in a text, the answer could be in table, the answer could be in images, it could be anywhere. Let's say you have this query that you start with. To do a proper multimodal RAG, keeping in mind two very important features of Gemini. One is the multimodal input, and the other is the 2 million context window. What you can do here is you just get the query. The step two is you get all the relevant text chunks across all the files. And I'm taking top 20 in this case. So I'm saying, hey, go through all the chunks of text that you have. Give me the top 20 using cosine similarity, which maps with each and every question. So you can send just one question or you can send 10 questions, doesn't matter, as long as you can get wider search area. So you can, if let's say you have 10 questions that you want the answer, you can keep the top n to, let's say, 30, 40, 100, whatever you think is the better top n is. So that's the step two. The step three, on the other hand, is you get all the relevant images also. So because you can do that, because you have the description of the images, what you say is that, hey, based on the question that I asked, go find all the images across all the documents that I have, and you're taking top 10 images. Then you write a very simple prompt, which is a RAG prompt, and then you sort of define certain instructions. You say that, hey, please analyze, synthesize, reason, and respond. You're giving some kind of a chain of thought reasoning infrastructure there so that it goes into detail while answering this. And then you also give it a specific output format. So you say that every output should have a question, answer, explanation, and the source from where the answer is coming. And what you do is you basically send all of this together. So you send all the text that you can find which are relevant to the questions that you ask. You throw all the images that you found that are relevant to all the questions that you ask. Again, at no point you're mentioning which file it is from. And because you want to get the citation, you are also passing the path of the image, the description, and the source of the text. So, where the file name is, what is the page number, and all of that. When you combine all of this together and you send all of this to Gemini 1.5, and again, do remember that you have 2 million contexts, you can actually send a huge amount of input to it. And this is where, even if you have limitations with the context, you will not be able to worry about that, because Gemini can process those 2 million. So this is what happens. So for example, now when you send all of that, you can see that how it goes through each and every question. It brings up those answers, it brings up the explanations, and the beauty is it also gives you where it found that information. So for example, if you notice this, the information, the question that we asked, the answer was actually available in a specific image, which is this one, which is, again, we didn't tell it where the image is. It was able to find out automatically from there. Similarly, if you were to wrap all of this, let's say, behind a function, here's another example of it, where I asked that specific question, and you can see that it was able to again find the answer, go through the explanations, and it tells me that, hey, this answer is available in this paper, which is .pdf, page number 18 and 19, and then figure 6 was used to bring to this answer. So this is amazing, right? Like, if you really think about this, this is very powerful, because your intelligence is sort of unbound in this sense. You can sort of add as much as possible because you don't have to worry about the context. That's where Gemini shines. You can also sort of input as much as possible from the modality perspective. So it could be audio, images, text, all of this sort of fused together and give you like a typical human input, right? Now, with that, I'm going to stop. There's lot many things that we can talk about, but given that this is a 1 hour session, let me stop, and let's take questions.